Okay, so Paul's running a little bit late from lecture, so I'll just start the seminar off. So welcome to the September 2018 FPGA seminar. Today we have Dr. Ziad Abouamer from University of Guelph. Dr. Abouamer is now currently a postdoc researcher at the Computer Engineering Department at the University of Guelph, where in April 2018 he received his PhD degree in computer engineering, advised by Professor Shaki Arabi. Previously, he received his master's degree from University of South Florida and his bachelor's degree from the University of Gaza in computer engineering as well. His research interests include CAD algorithms and architectures for FPGAs and digital circuits, and today he'll be talking about GPlace3.0.
Thank you for the introductions. Just I want to give you a little bit of the context about the topic. We started in 2016 by participating in the competition in Routability-Driven analytic tracer organized by ISPD. And at the time we finished at the 3rd place. And since then we did lots of modifications and enhancements to the flow. And that's what the outcome of that GPlace3.0 for a routability-driven FPGA placement for targeting UltraScale architectures. And the outline, I'll start with some background and motivations. Then I'll introduce or explain the GPlace flow for routability-driven, as well as some other current and future works. So the traditional FPGA CAD flow actually separates the back-end stages like backing, placement, routing to simplify the complexity. However, like doing logical backing without taking into consideration the physical locations of the lots, it may introduce a poor backed netlist that restrict the placement solution, as well as a dense CLB backing may introduce congestion problems. So we introduced like a GPlace3.0 that simultaneously tackle backing the placement at the same time and dealing with the flat technology map netlist and perform placement without explicit backing stage. The motivation behind the work starts in 2016 when we participated in the competition organized by ISPD and sponsored by Xilinx, targeting the latest architecture at the time and evaluated by Industrial Flow, Vivado. And that competition focused on more complicated legalization rules, as well as routing congestion. So this is the device that we target, which is Vertex UltraScale with a 20 nanometer technology. This is one single die. Also, the benchmark that we evaluated based on is 12 benchmarks with a variety of utilizations, reaching a high utilization of LUTs, flip-flops, DSPs, and block ramps, with the largest design reached to 1.1 million instances, as well as having a large combination of clocks, reset, and clock-enabled signals that imposes more constraints to the placement engine, as well as having some very complicated interconnections for some circuits with the rate exponent reached to 0.8. Now, this figure will show how the bookshelf benchmark generated and how the academic placer evaluated in this competition. So we start with the structure of Verilog, get into the Vivado stack for logic synthesis, followed by placing the I/O, and then writing the bookshelf format for the design, as well as having a checkpoint to read it again when we do the routing. So we perform the academic placers, produce like a simple format for placement results, using the batch file to read that simple format of placement results in Vivado, and then check the legality, and you run the detailed router by Xilinx or Vivado to get the routed wire length and evaluate, have a comparison between different academic placers based on routed wire length. So this is just an introduction or like explanation of the legalization rules and backing for the UltraScale FPGAs. This is a simple layout for the UltraScale architecture with different heterogeneous components. If we look to the slice here, or a CLB, you can see it, okay, it contains like 6 lookup tables, 6 input lookup tables, and 16 flip-flops. Each 6 input lookup tables is a fractional lots where you can implement 2 different functions with at most 5 distinct inputs. Also, the flip-flops are divided into 2 groups. Each group should share the same clock and reset signals, and each group is subdivided into subgroups. Each of subgroups of 4 flip-flops share the same clock-enabled signals. So while you do the placement, you need to satisfy all these constraints when you do the bipartition or legalization for flip-flops. Problems definition is placement. We take a flat technology map netlist, we map it into the proper locations in the FPGA while we're meeting all these hard constraints as well as optimizing for several methods. Now, to summarize, with multiple resource constraints as well as multiple conflict objectives, now in the competition we focus only on congestion and routability and wirelength only, not timing, and high compilation time, and with complicated like benchmarks for routability with high rent exponent, lots of combination of control signals, and large utilizations. Even like Vivado 15.4 fails on having a solution that's routable for the largest 2 benchmarks.
A question, since you're showing rent exponents, does that mean these are synthetically generated circuits?
Yeah.
Okay.
Yeah, it's synthetically generated. But later on, we have some results for some industrial benchmark. That motivates us to have to look again for different strategies for placement. Now we look back to the previous work on backing placement. So traditionally they do start with fully backing, logical backing, then they do the placement and legalization. Like for example VBR or any previous analytic placers, they do the same thing. So the issue with the logical backing, it may back something that is actually far apart. So that will restrict a lot the placement solution. Now another way is having or running a flat initial placement first, then perform a placement-aware backing to guide the backing and having a full CLB netlist, and then perform global placement and legalization. And 2 examples of those is UTPlace, placed first in the competition, as well as GPlace3.0, which is placed third in the competition. The drawback for this is the flat initial placement ignores all the backing and legalization rules. So if you have lots of those rules, the solution that's generated by the flat initial placement is sometimes it's far away from the legal final solution. And also when you do the backing, BLE and CLB backing, you need to average the locations or the positions of the cells that is contained to find the new position of the CLBs and BLE. That will restrict or degrade the solution quality. Another way is just perform flat initial placement and then do semi-backing, not fully backing, to BLE, and then perform a global placement and finally legalize. Now here, the same issue with all the previous technique with the flat initial placement, because it doesn't consider any backing rules. Also here, sometimes in some cases with high utilization of the design, then you need to sometimes break those BLE backing to find a legal solution. One example is using Rebel FPGA, which is placed second in the competition. So we come up with a new methodology or new technique for placement, which is flat all the way. So just we incorporate all the legalization rules within the bipartition legalization during the global placement. So we work with a flat lot flip-flops netlist. We accommodate those legalization rules while we do the global placement. So every time we have a legal solution here. And this work doesn't have like an explicit backing stage. So each iteration, the flip-flop and lots, it's free to move to find a different optimal locations. And this work is submitted in ACM in November 2017 and accepted in June. So the idea here is early backing may hurt the placement if we do the early backing of lots and flip-flops, restrict the placement. So the idea here is we incorporate all those control signals and lot sharing while we do the bipartition. So the flow of the GPlace3 has like 3 phases. The first phase is just to produce a wirelength high-quality wirelength placement. So we have a wirelength-driven global placement, then followed by estimating the congestion, inflating the lines or cells, and having a congestion-aware global placement to optimize for congestion. Then followed by another technique with dual objective ISM, independent set matching, that alternatively optimize for 2 different objectives, external bands and estimated wire length to improve, further improve for both wire length and routability. This will show an example of illustrating the examples of one of the examples through the phases. So in phase 1, we optimize for the estimated wire length, but we end up with highly congested placement because we only focus on wire length. Now, after estimating the congestion, inflating the cells, we increase the estimated wire length a little bit, but we have a better or less congested heat map. After performing the detailed placement, we improve both estimated wire length as well as the less congested heat map. So to look into details for each phase, the goal for wirelength-driven global placement is optimizing for wire length. So we cannot tackle the congestion before having a good wire length placement. So we start with bin propagation because the I/O is fixed. So we place the cells closer to their I/O first. Then we use analytic placer with a star plus model solved by Jacobi solvers, followed by bipartition legalization, recursive bipartition legalization. Now, in the bipartition legalization, we should incorporate all the backing and legalization rules while we do the bipartition to have a legal placement solution. So here, after that, we have a completely legal placement solution, but optimized only for wire length. So this starts with finding a minimum window by clustering adjacent cells into groups. Then we expand that window until we have like enough or resources, maybe similar to the SymBL approach. And if we have a merge, overlapped window, then we merge them together and we spread we perform bipartition for different components later on. Now, before we legalize the lots, we have an issue here because there is a dependency between the lot sharing and the lot capacity or the slice capacity for lots. What I mean by that is the slice can contain like 8 lots if there are 6 inputs, or up to 16 lots if they are smaller and can be shareable. So to overcome this problem, we just after solving, having the solution from the solver, based on A distance and maximum sharing, we can bear some lots, and then we remove them from the net list and do the bipartitioning based on the a capacity of 8 lots. After that, we remove the lots back to the net list. So next time when we solve those lots that are shared in this iteration, it can be breaking the sharing to find different optimal solution and so on.
So in this case, for each pair of LUTs, you get rid of one of the pair,
Yeah, to have just only capacity of 8 for
and
each
then
slot.
when you place that single
We
one
place
into a
it with
slot,
that shared lot.
and then that implies the placement of the pair.
Yes. And next time, when we solve, those lots are free to break.
Okay.
So you do the LUT sharing after you've created your
After-
illegal placement, basically. So you choose two that are nearby that
Yeah,
are
with maximum sharing.
that are pairable, basically, like they're
Correct,
legally
yes.
pairable.
Before that, we have a hash table that have all the combinations for shareable, so we can do that very quickly.
Sure, and all the combinations are legal, so you enforce legality constraints there.
Yes. So then the lot by partitioning DSP block RAMs becomes very similar. The only difference is the capacity is different. 8 for example, the lot for DSP and block RAMs is 1 for each side. So recursive by partitioning is traditional one, which is breaking the FPGA into half and moving like cells from overlap or overflowing region to another based on minimizing the displacement and with different capacity constraints. Now the thing is how we deal with the constraints of the flip-flops while we do the bipartition. Okay, now just to recap, like we can have up to 16 flip-flops if they are all shareable, for example, and each slice can have like 2 groups. Each group has same combination of clock and reset signals. Each group can be divided into 4 like flip-flops or 2 subgroups with 4 flip-flops. But these flip-flops and subgroups, they should share the same clock enable signals. So we need to have some data structure and a way to compute the, like if you have like flip-flops in this region, we need to compute it efficiently. How many exactly what's the number of slices required to satisfy all those constraints of the flip-flops. And also when we move flip-flops from one region to another, we need to update that number of slices. So to do that, we maintain like a tree structure. So for example, if we have like those 37 flip-flops in region 0, we need to identify if this region is overflowing or not. So here, by having this tree at the beginning, so this means this 9 flip-flops share the same clock enable and having the same combination of clock reset signals and so on. So we traverse the tree from bottom up to calculate the exact number of slices. So by dividing the number of flip-flops into 4, so we know how many subgroups we need actually for those flip-flops. Correct? Then we add those subgroups that share the same clock reset signal, divide them by 2 because each group it has 2 subgroups. Okay. So we end up. This is the number of groups or half slices required. Now we add them together and divide it by 2, so we end up with what's the exact number of slices required. Now if we ignore the control signals, now we have 37, correct? Divided by 16, so we need up to like 3 slices is enough to accommodate those, correct? But actually to have a legal solution, we need 4 slices. Now if we have a large combination of clock reset, clock enable signals, we have a big difference between ignoring those rules and focus only on capacity alone. That's the outcome of the phase 1, highly congested placement. Now the next time is we need to identify the congestion. We introduce a novel modification of the ASIC global router. We perform pathfinder, but we use the same cost function that is used for the ASIC global router, and use it within the pathfinder after modifying some of the cost functions. And we end up with, this is the wirelength per area. This is the cost function that's used in PBR with only focus on wire length cost. And also this is a cost function that is used for the ASIC router. This is the modified cost function for a global router. And this is the detailed router heat map after we extracting the congestion, after doing the detailed router and extracting that using TickleScript. Based on this figure, as well as the table that shows some similarity metrics to measure the similarity, we found that this is the most closer to the true detailed router congestion heat map. Now this is shows the equations that is used for the ASIC global router. The only thing that we modify is we adaptively modify the cost of the present cost, and that's not adaptive by time, but also it's adaptive by the progress of the global router.
Can I ask a question? Just go back one slide.
Yes.
So you're using global routing here, so the BPR Pathfinder and NTU GR are you basically doing global routing only? Is that correct?
Pathfinder, but we use different congestion,
Okay.
different
And then you're comparing that to MPF GR is your global router or your predictor?
This is our global router by modifying the cost function.
Okay, so that's also, so all three in the middle are global routing.
Yeah, all of them Pathfinder.
WLPA is,
Wirelength per area.
it's wire, okay, so it's just divide, you
Yeah,
divide
yeah.
basically the wire length of the bins, okay? And then the last one is the bottom detail.
Yes.
Thank you.
Okay, so we adapt the present cost like by the progress of the router. And we found that this is like two benchmarks, but the behavior is similar for the 12 synthetic benchmarks. Okay, so if we look to the FPGA 1, for example, here, this will show us two things, like the overflows as well as the wire length. So this three curves actually showing the overflows for the cost function if we use the same one for VBR, cost function that use for ASIC and for ours. Okay, so we found that VBR cost function is quickly get rid of the overflows, but it has overshooting for the wire length. Now here, the second one for ours, so we get rid of the overflows quicker than the ASIC cost function by adding that adaptive present cost function. As well as here, if we see, this is the brown is our wire length. So we end up with, so we get rid of the overflows quickly, but we end up with better wire length at the end also. Also here for highly congested benchmark that has a 0.8 rent exponent, you see here our wire length compared to the ASIC cost actually is a little bit higher, but if you see the overflows, we're able to get rid of most of the overflows, but the ASIC cost from a global router cost function actually is stuck somewhere, so it's not able to get rid of the overflows. Not clear?
So the left
definite-
axis is overflow and the right axis is wire length, is that correct?
Yeah, this is the overflow, this is the wire length. These three, this one is the overflow. These three is the wire length.
Okay,
It's very complicated.
so the difference in wire length is small, the difference in overflow is large. Like the axis on the right basically is a relatively small range, but the axis on the left is a very big range, is that right?
Oh, you mean the different ranges? Yes, the
Okay.
different ranges. Yes. But the idea here is, you see that we are conservative with adding, like increasing the wire length, but also the job for the global router should get rid of the overflows. But here we found that for hard to route designs, the original cost function actually is not able to get rid of those overflows. stuck in.
And just on the definition of overflow here, Ziad.
Oh, okay. So the definition is when you do the routing,
Yeah.
you
So
have
do you assume W tracks per channel?
you have a channel
Okay.
capacity.
And you assume that your overflow means you exceeded the total number of tracks per channel?
Yeah, the capacity for that edge is more, for example, is less than the demand. So you have overflow.
So that doesn't take into account the switch block connectivity or anything like that. It assumes
No,
anything.
no, that's global. Yeah,
Right,
anything
so-
within the switch, we ignore it. So actually, we extract the from the UltraScale device, we extract the global connectivity.
So it's just the total number of tracks per channel.
Yeah, we extract the global connectivity. We draw the graph resources based on the global connectivity only. But we address, oh yeah, it's a good point because it's explained in the paper, but not here, that because we have some limited connectivity within the switch,
Right.
so we add some approximation actually to this. Approximation of based on the pin count within the time.
So you sort
to
of scale
reduce
down
the-
the capacity.
Scale down.
What do you scale it down to? What do you find works well?
Hmm?
What do you scale it down to?
Like, do you scale it down by
70%,
30% or something? Or-
It depends. It's a variable of the pin count. So some constant that's fixed always multiplied by a pin count.
So a pin count of a switch block.
That's in the time. Yeah, in the switch.
So in the device architecture.
Yeah. So that's the. And this work I think it's I read it before in one of the techniques in ASIC. They use something similar. And they found that that's independent of technology actually. That's why it may work for different technology. I don't remember exactly the paper, but it's close like that. So after estimating the congestion, we apply lot inflations. We identify the congestion. We apply lot inflation based on simple formula. This S factor actually based on the congestion value in that location, as well as the total congestion for the complete benchmark. So it's captured both two things. Simple equation. Then we perform the legalization to the area, the virtual area of the lots. So we explain this soon. So all these blocks actually very similar to the previous phase, except that when we do the lot by partition, we should take into consideration that we have different virtual area of different lots. So we introduced different constraints here. One is hard constraint that should be met so that we end up with legal solution. Another, so the hard constraint actually, each partition, assume that, for example, each side accommodates only one lot, okay, for simplicity. Now, number of lots in that partition should end up with less or equal to the number of sides. Otherwise, the hard constraint is not met, and we have to accommodate that. Now, the soft constraint is after inflation, the area, the virtual area of the lots actually increased. So we try to accommodate, like, now here we have, for example, an area of 4 for those, but we have only 3 sides. So we have overflow. So we try to balance this as much as possible. Sometimes it's not possible if you inflate more than necessary. Okay. If we are not able to do that, we try to balance when we do the bipartitioning, balance the area of the lots. But we keep to have like a displacement constraints, minimizing the displacement. So this is an example, a quick example. So if we start with an area of, for each lot is 1, after we inflate, let's say we inflate, for example, C and D becomes an area of 2. So this partition is having a soft constraint that's not satisfied. If we move, like, for example, the one that is closest to the edge, to the right partition, we able to satisfy both of them. Okay. And this is the output of the second phase. Okay. Now, Now for the detailed placement,
Like, can I ask you a question?
Yeah.
So, I don't know if I'm understanding the algorithm perfectly or not. I think you're basically inflating LUTs by local metrics. Basically, their pin count relative to the total density of pins throughout the circuit. Is that correct?
no,
Or are
it's
you
not-
inflating the
no,
LUTs
no.
based on congestion information? in case
Congestion
you move the
information,
router?
yeah. Okay, so
So
I
what
didn't
was the
explain that.
link? Where did you?
Okay, so here, this one, I didn't show the equation for computing this factor.
So S is based
So
on
this
the
based
congestion.
on the congestion value.
Okay.
Congestion, because we already applied the global router, so we know the congestion value.
Okay. So S comes from your
Yeah,
global
but
router.
also it has some like portion of what's the total congestion, I mean the congestion in total also. Because sometimes you have a congestion value similar for a different placement, but maybe those two benchmarks are not having the same difficulty for routing.
Sure.
So
So,
we-
because my interpretation of this is the S is your
Yes.
congestion map.
Correct.
It's how congested you are relative to the global congestion, and your inputs LUTs plus outputs LUTs divided by ratio of U LUT. I'm guessing ratio U LUT is
This
the
is a
average
fixed
inputs.
one, it's fixed constant,
Okay.
and this one is the mean, like the average number of inputs or lots.
Okay. So the
Based
basically
on
a
the
local
distribution.
congestion metric. You've got a pin density metric relative to the average. You've got a congestion metric from your global router relative to the average.
Yes, correct.
Thanks.
Other equations actually in the paper, and it should appear, I think, in October. Now after, okay, we applied the detailed placement using independent set matching. The idea of independent set matching, then you do the like bipartite matching to find the optimal moves, but you wanna make sure that the blocks that you picked are not connected to each other. So you guarantee that you find an optimal movement for this. Now this figure shows only a CLB, but actually okay, so this is, okay. Also we incorporate white space to have a larger search space. We have a different, like independence for different level. Like we do that for CLBs, flip-flops, or flip-flops alone, lots alone. Okay. Why are we doing that? Because if we only just moving lots and flip-flop, we end up with a stack somewhere in local minimum. By moving a group of lots and flip-flop with CLBs, you can help to scale local minima to find or jump to a different solution locations, so you can keep moving, like optimizing for lots and flip-flops to escape the local minima. Okay. Now the issue here with our flow is we are not doing any backing, explicit backing. So we may end up with a CLB that doesn't have a strong connectivity between lots and flip-flops within that CLB, because we are not having a complete like or explicit backing stage. So we apply a novel technique that alternate between minimizing external bends and minimizing wire length, and alternate between them to help to improve the clusters within the CLB and then move to optimize for wire length. And that will help us to escape the local minimum more efficiently. So again, here we, for example, we may start minimizing the external bend. Now external bends is like the bends that's outside the CLB. Okay, so not any bends that can be routed within the CLB is excluded. So by minimizing external bends, indirectly you optimize for or minimize the external nets between them. And that also will help the router, so having less effort by the router to route the external nets. But the most interesting thing is, because the CLBs, interconnections between CLBs, if you are not doing explicit packing, you have lots of interconnections between CLBs. That makes movement, the movement of the CLB is very restricted. Okay, So we try to optimize or minimize the external bands so that we reduce the interconnection between the CLBs, as well as we make the connections within the CLBs more stronger. So this makes the movement of the CLB more effective and efficient. And we do that, then we apply like optimizing for wire length in a hierarchical fashion, CLBs, loss and flip-flops, so that will optimize more. One thing that we can mention here is sometimes optimizing for external band may ruin that. We can limit it to not ruin the wire length, but this is at the beginning is very restricted. So we have some threshold at the beginning. So we can optimize for minimizing the external bands if you within that threshold of ruining the wire length. And later on, because we alternate between them for multiple iterations, later on we keep reducing that threshold until we only optimize for wire length or external bands while not ruining the wire length. And we find that this is like, I have a table, but not here, maybe, that shows the difference if we remove this and only optimize for wire length. And we find that it's like around 3% improvement. Now for results, we use 12 benchmarks in the competition as well as, yes.
Just one quick question. It must be happening somewhere, but let's say you have many. You're going to have many cases of a LUT directly driving the flip flop, and you have to sort of that you mandatory it. You have to pack those side by side. Okay. So doesn't that create situations where you'll have a LUT and it directly drives the flip flop, but the flip flop is not in the adjacent part of the slice, meaning in that sort of
within the slice?
Yeah.
Within the slice, yeah. That's actually, in the old GPlace, we try to align those. So we have them in the same BLE.
Sure,
That's
so
right,
BLE, yeah.
But for this one, I think I removed that. It doesn't make a difference, actually.
So this UltraScale architecture, you can just come in separately and hit the flip flop?
Yeah, you have lots of resources, actually, that make that constraint maybe
Less important?
less important. I think so. Also, we have results of time later on that shows that
Yeah.
timing driven.
Yeah, I would think that would whack your timing if you don't.
Actually, we keep it flat and we surprised with the results. Okay. Now here this is also still like synthetic 372 benchmarks provided by Xilinx.
Do you know how GNL works? Like, it's a known hard problem to produce realistic benchmarks.
Mhm.
So do you know how generate netlist works? Like, what is
Yeah, I asked them actually, but they said that they did lots of modifications because that one it's basically was like for ASIC, generating circuits for ASIC. So they told me that they did lots of internal modification to GNL, and they use it internally. We able just to get we get that benchmark from them. That's the only thing. Okay, so now here comparing to the state-of-the-art academic places, UT and Rebel from Texas, Austin, and Hong Kong. We have less failures in terms of theorems. Like 70% of the time we have a best routed learning. And actually this GPlace is only, on all of them actually, they only tuned in the 12 benchmark. But maybe there is some similarity between the 12 benchmark and 372. Make it also maybe. You don't need to tune it for the other benchmarks because they are generated from the station. And on average, we have like 5% and 14% better routed wire length, faster runtime placer, and more interestingly, actually, also faster because we have less congested placements. Maybe the other teams they try to have a much better routed wire length, and so I have it on the edge of the routing. So that's why in some benchmarks they are barely routed. Now for Fmax, that's of course like maybe those actually non-driven, non-time driven placers, but we collect the Fmax for those routability-driven placers, and we found that like UT and Rebel actually failed to route because in Vivado it will not tell you what's the maximum frequency based on the placement. You need to run the router with different frequency, and each time the router will make its like the best effort to meet the timing. So when we do that, actually we do a binary search to speed it up, and we went by like 0.1 nanosecond as a step. And once we reach using binary search, sometimes you are not lucky because you divide it by some fractions or whatever. So when we reach the point where, okay, it's satisfied with this is the minimum one, so we run a sequential search around that point to just double check that we are not like unlucky in some points, okay? So it takes lots of time to generate this results. So and we stop if we like have a very low maximum frequency, then we stop and treat it as not routable. So and that's the case for FPGA, for Rebel and UT. And on average, actually, we have a better, and surprisingly, actually, they do backing. So they take care of not flip-flop alignment.
The other two.
The two, yeah. And maybe it's plus. Yeah. And for the same solution here, we check, okay, what about for that same solution, we look to the routed wirelength based on timing driven detailed router. And we still have a better routed wirelength. This is to compare with non-timing driven divider placer 15.4 in the synthetic benchmark. Fill them 3, and we have a better 3%. Now for a routed wirelength, also we still have a better 14% better routed wirelength. Now to compare it with timing driven, it's okay. This is because they have an issue with the routability issue with high utilization of benchmarks in this version. And maybe because it's synthetic, I'm not sure. Here we are 20% worse in Fmax. That makes sense because we are not optimizing for timing. Okay. And if we look to the routed wire length, but we have very conservative like routed wire length. So we have lots of room to beyond like the wire length, sacrifice the wire length to optimize for time. Okay. Now let's go to the timing. This is like continuing work. It's not finished yet, but we have a surprising results actually for timing driven. Actually, those previous results we are asked by the reviewers to have timing information, and maybe by luck we get very good results for that. Okay, so now for timing driven, now we need to remember that we don't have the delay models for the architecture, so we need to extract this. It takes a long time to extract those delay models, and also it's very complicated. Between different distances, you have different delay models based on different pin, different locations within the slice. But we have like some good way to have a good estimation and manage to have a very compact lookup table for the delay using some patterns that is in that architecture. Also, we modeled the delay within the cells, and we implemented the static timing analysis and incorporate timing in different stages. This is just modification for the stages, and we add at the end because those timing optimization is net-based optimization, and we added at the end, it makes, I think, sense having a path-based optimization for timing optimization at the end. And we keep it flat all the way. So we're not worried about packing lots together. And we have the results for the old Vivado and the new Vivado for timing. We are the best in terms of Fmax for 8 out of 12 benchmarks, and on average, I think 8% better Fmax. I don't have the routed wirelength, but we have also better routed wirelength as well. Yes.
Is your timing driven version tied to match flip-flop left pairs or no?
These circuits are, it looks like
Yeah.
lots of them are incredibly slow considering it's UltraScale and 20 nanometer, but some of the circuits are only running at 50 megahertz. So my guess is that these are not deeply pipelined. They have long,
but also,
long combinational paths.
also here,
These are the
we have a
ISPD.
restricted component, and there is no carried chain and stuff like that.
Oh,
Open,
So
okay.
yeah,
Oh,
no
okay,
carried
okay,
chains.
okay, I see.
So only lookup tables, flip-flops, DSPs, programs,
I see.
input buffer, output buffer, load buffers,
So they're still randomly generated?
randomly
Okay.
by them. So, of course, now the question is, what about a real industrial benchmark? That may be more interesting. But also here, we need to, okay, let's move to another topic if we don't have a question, and then move back to the industrial benchmark generator. Okay. Any questions here? Or? Actually, we are running for some industrial benchmark, but we don't have enough time to present them. Maybe later on. But we're able to generate some real benchmarks in the same.
Those have carry chains, etc. in them.
Not carry chain, because our placer is still not handling carry chains.
Yeah,
So that's a
important
limitation.
Because I mean, all designs have carry chains, right? So,
Yeah, but you can have an option with Vivado, the new Vivado actually, to get rid of the carry chain.
Sure.
And implement it and muxes and implement it in a different way.
you can, but typically that slows the circuit down a lot.
Correct, but
So-
that's for all the placers, not only for Vivado. For ours and for Vivado at the same time. I know right now at that point is maybe it's the first step. You can't jump.
Sure,
just to
no,
that.
it's promising results.
This looks good, yeah.
Now for machine learning congestion estimation, actually this paper is presented recently in FDL and get the best paper award. Very simple, but I think it's effective also. Now here, instead of doing global router to estimate the congestion, which is the heat map, it takes like maybe 15 to 20% of our flow. And if we use global router frequently, maybe it takes more than that. So can we do that, estimate those or predict those heat maps using machine learning? If you look to the picture, okay, it's similar to image processing or whatever. So it's maybe very suitable for machine learning to predict those heat maps. So we use a supervised machine learning where we use the training set to to estimate the prediction function to map the input features to the output labels. After that, we use the testing using the mapping function. Based on the inputs, we get the congestion value or the predicted value. Now here Now here for each G cell, we collect 4 features in each G cell that covering a switch. The first feature is wirelength per area. So for this highlighted G cell, based on the net that is covered, the G cell, we compute the wirelength per area for that net. Okay, so we end up with 5 divided by 12. Okay. Now the wirelength per area doesn't represent or model the local routing. So to capture the local routing, we have a second feature using a pin count or pin density. And this is 3 focus highlighted features related to G7. The third and fourth feature is netcut per region with different size window. This is an example of window 3 by 3, but we use 5 by 5 and 9 by 9 in our net features. And the leaving nets actually is 2, so the netcut per region for window 3 by 3 is 2. Now, okay, we use the 372 benchmarks, we place them. Now we get the binaries also from other teams. So we have different placers, we have different versions of GPlace, so we able to get like maybe 5,000 different placement. We can do more, but maybe it's enough right now. 5,000 different placement. We extract the features for those. We run the routing for all of them. And then we write a tickle script that extract the routing tree for each net and compute the utilization for each tile or switch. Yes?
You said you have 5,000 different placements, but it's based on 372 benchmarks?
Yeah, because the congestion is not based on benchmark only. It's based on benchmark and how you place it also.
But do you feel that if you're using these placement results, they would have some correlation with that?
No, because of 2 things. One is you can have the same circuit and place it very badly to have a very different congestion map. And you can have it like very relaxed, blah, blah, and have totally different shape, different congestion value at all. And if you look the same, I mean, if you look at the heat map, high quality maybe academic placers like UT, Rebel, and GPlace, they are totally different for the same placement. But also you can take some placement in the middle of the flow to have it very highly congested or something like that. So you have a very wide range of placements. Okay, this is one thing. Another thing is, after we extract and have a congestion value for each, we use it as a label. And here, if we look to the row, each row in the data set actually is a switch box. It's not, we are dealing with the fine grain when we do the training. So you end up with maybe like 28 million records in the data set. We're not taking that into a complete picture, but we use those features to capture some global informations. And we do at the end some smoothing to get some global information from neighbor switches. We do the filtering by taking off the switches that are not used by the router, so it's not confusing the model. Then we train it with different models, but we end up with using linear regression model. Then for a testing circuit, we just place it, get the features, apply the linear model, get the heat map, and we deploy it into GPlace instead of the global router. And this is the results actually here. Our machine learning is even sometimes better than global router.
So this is also from different benchmarks than the one you trained on, or are
Yeah. Of course, we split them. We use also now for more details actually. Because some benchmarks are very similar to each other, so we try to pick 2 sets that are totally different in terms of characteristics of the benchmark, like FPGA 10 and something that is closer to it. We put it in the testing. This is one thing. Another thing is we exclude one of the placers, like for example UT. Any placement that's generated by UT, we put them all in the testing. It's not incorporated in the training, just to have like more like unseen placement. Okay. Now we have a full factorial features. And if we combine them, we have like 83% of R square. Okay. Now, to improve that, we do some smoothing with 5x5 window filters here to smooth the netcut per region 5x5. And we're able to improve the accuracy a little bit. Because, of course, again, having global information will help lots. Okay, and compare it with CFPR, I think, work from Hong Kong, in ICCAD 2017. It's totally different than the third router here, their model. And we have like a better by 25% better. Now this shows like if we incorporate that into GPlace, we have similar, almost similar results that what we get in using global router. But of course, this is the runtime for the machine learning, which is fractions of seconds, and this is like a global router for some cases, like each like close to 300. Okay. That's the award that we get for that FPGA paper. Now, let's move here.
So in the case that you gave, say, the default router in bad placement, the bad placement, I mean, low router, you just take the congestion map from the low router and use it to train your.
No, that's an issue. So for those cases, we try to avoid those cases as much as possible, but you can get the results from the global router. Because I think I'm not sure, like in the router, if it's not routed, then you don't have the information for the unroutable links. Correct? How do you know where? It's based on if it's close to routing, that's okay. But if it's from the beginning, it's not routable, how you can get through that?
So in that case, you can use the global
You
router.
can use the global router, assuming that that's good enough. Now for what about the industrial benchmark? Can we have the similar results, different? Now we have a restriction here because the academic placers that we have, 3 academic placers, UT, GPlace, Rebel, all of them handles only the bookshelf components and format. So we take the HDL or high level synthesis, but we try to generate a circuit because we need to keep the same functionality of the circuit. We don't want to change the functionality of the circuit, but we need to have the same only a bookshelf like component. These are the only component that we handle. We can handle also different flip-flop types, different lots, those buffers, but no carry chain, no muxes, some other stuff. So that's a challenging when you do keep the same functionality as well as having only those components. So we found that the new Vivado, it has more options and constraints that we can apply it as a block constraints. So we write some wrappers to the original design to have one block. If we have a separate blocks and apply those constraints and options in the synthesizer for the top level block. And we found that there is some useful parameters here that we can use to generate only bookshelf netlist that have the same components in the competition. Okay, that's what we have right now. So, so we take the HDL or maybe high-level synthesis, synthesize it, and then synthesize it the new Vivado here. Place the I/O because right now we are fixing the I/O, but StarPlus and GPlace is able to move the I/O easily. Then we write the ADIF. Now here we do some changes to the ADIF, but doesn't change the that's because if we have okay now we do the synthesizing in Vivado. Sometimes it already pairs the lots together. Like these two should be paired together, blah, 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 and it's written in the EDIF. And when you read it back, it forces you to place it in those together again. So we remove that from the EDIF, so we have flexibility to break those suggested sharing from Vivado. Another thing is some of the lots will have like two inputs that's connected to same input, or not same input, like it's connected to VDD and ground. One of the inputs is connected to VDD and ground, but it's in the circuit. So, and if we, okay, what is the source for the VDD and ground? If we put it like here in the FPGA, this is not true because VDD and ground can be supplied from a switch. There is a source in the switch box that gives the VDD and ground. So we need to get rid of those, shrink the size of the lot for those, like, because if you have a constant for one lot, you can treat it as, instead of 3 input lots, you can treat it as 2 input lots and so on. We do this modification here, and then we read it into Vivado. Why Vivado 15.4? Because we have the patch to read and write to those academic placers. But we can easily later on having this patch for the new Vivado, so we get rid of this new old flow. And then we write a tickle script that extract, after you read the design in the old Vivado, we extract the bookshelf as well as the checkpoint. By doing that, we're able to get 2 benchmarks from Titan. Actually, the Gaussian blur is not from Titan, it's from the HLS. We have an issue with synthesizing the Titan HDL for Gaussian blur in Vivado. It takes a long time, I don't know what. But so we find a code for C code for Gaussian blur, play with the directives to generate the size of critical size for the design. This is the statistics for, and now for Bitcoin miner, we have like 2 different implementation, one pipeline, the other is not. And you can also have like multiple cores, like 4 cores, 6 cores, to have different sizes of that same design. Okay. And we're able to generate a bookshelf benchmark for those 2 largest 2. And we run it, compare it with Vivado 15.4 and routed wirelength. Now the conclusion is a little bit different, but it's not far. Maybe there is a restriction by using only those components in the Vivado, but it's still competitive actually. And we are not, this is just, we are not doing any tuning towards these benchmarks. We just run it as is with those 2 benchmarks. Now for timing, for timing it's still running, but it takes time. Unfortunately, it's not ready for this talk. Yeah. Conclusions. We have, I think, the first, to my knowledge, the first like flat placers that have without explicit backing stage. State of the art, like for routed wirelength, and also for timing driven. This is still continuing work, and I think we have some room for more improvement, but maybe not much. Okay, so and also machine learning, congestion estimation, and a website for a benchmark, and also maybe the binaries and stuff like that. But I think it's not ready now. Maybe within 2 or after 2 weeks. This is the URL, so you can check it maybe after 2 weeks. We have all the 372 benchmarks. So maybe if we have also benchmarks for industrial one later on, we'll have it there, as well as the binaries. The future work is now working on like supporting more components, make it more realistic. It's challenging. It's legalization rules becomes maybe more complicated now, but hopefully and also supporting multiple clocks. Right now we only support one clock per design. And also targeting the UltraScale Plus with the 2.5D or 3D, okay, with the 10 dots. And hopefully we can get the benchmark from one of the companies, real. Actually, we have already talked or have some talks with some company. Maybe they will provide us large designs to test it and thank you very much.
Any questions? I think everybody's feet up. Okay, so just before we break, so I'll just say that thanks to Kaveh here from Jump Trading, who sponsored